In the next three chapters, we'll look at later stage hydrothermal or burial dolomites, where their geochemistry tends to indicate they formed in deeper and hotter mesogenetic or burial realms from the crossflows, often the focus crossflows of fluids flowing under the influence of temperature and pressure contrasts. There are a range of settings where we develop burial hydrologies facilitating the formation of these later stage, hotter dolomites. It can be the escape of compactional waters. It can be due to deep meteoric circulation or topographic recharge driving waters deeper into the burial realm. It can relate to faulting, such as we get when we have a series of thrust-related squeeze belts tied to fluid escape focused along the thrust system. Or it can be related to thermal convection, where we emplace a heat source, such as an igneous mass. So these are the main realms where we can form late-stage warm fluid dolomites. It's interesting if we go back to our discussion of the mixing zone dolomites and we have a look at the Wisconsin Arch once again. And this is where Badziamani back in 1973 did his original doctoral work on the Durag or the mixing zone dolomites, which he argued were an association of dolomites not tied to evaporites and tied to the development of a mixing coastal zone, and so hence tied to a development of subaerial exposure. But when Lusjak went back in with another doctoral study and looked at the same dolomites and defined the maximum extent of the meteoric mixing zone as it could have existed atop the Wisconsin Arch versus the extent of the actual dolomite distribution, he found that these dolomites are much more likely to be not mixing zone dolomites, but a response to the crossflow of later, warmer burial fluids. And we'll look at the evidence for that throughout the next three chapters. If we compare and contrast the mixing zone dolomitisation of Badziamani for the Wisconsin Arch with the hydrothermal dolomite characteristics of the Wisconsin Arch, Badziamani noted that there was a regional distribution along bands that paralleled the Wisconsin Arch where we had subaerial exposure, and he argued mixing zones would develop along structural highs. In contrast, Luxjig argued that we have complete 100% dolomitisation east of the arch regardless of the structural position, as well as partial to complete dolomitisation along the arch and sporadic dolomitisation west of the arch, not geometries that one would expect to be associated with mixing zones. Badziamani noted that the dolomite replacement and precipitation was simultaneous with calcite dissolution in what he inferred was a mixing zone. Luxjig found that the dolomitized region extended well into the Michigan Basin, and that the dolomite replacement and precipitation was intimately associated with Mississippi Valley type late-stage burial dolomitization, with these dolomites in places acted as the host phase for the lead-zinc mineralization. For the fluid inclusions, we should be seeing homogenization temperatures of less than 50 degrees if we're looking at a coastal parallel mixing zone. What we actually see in the dolomites across the Wisconsin Arch and further to the east is homogenization temperatures which are much warmer, between 82 and 100 degrees centigrade. In addition, we found a broad range of oxygen isotope value, much more negative than would be expected if we were looking for a mixing zone dolomite. So in this original type area for mixing zone dolomitization, as argued for the Durag model by Badziamani, we now tend to interpret those same dolomites as later stage burial-related dolomites. There may have been an earlier mixing zone stage, but the predominant signature and the dominant outcome that formed these sparry dolomites across the arch and beyond is a hydrothermal association, not an early eogenetic mixing zone. So what are the characteristics of burial dolomites? Well, they tend to be coarsely crystalline cements, and they include a very characteristic morphology of dolomite, which is known as saddle dolomite. They tend to occur as vug and fracture fillings, which can constitute between 1 and 5% of the total rock volume, but can locally constitute 100% of the dolomite. If we look at the temperatures, the homogenization temperatures are quite warm, ranging from 80 to 200 degrees centigrade, and the waters from which they form We're looking at variations between 18 and hypersaline 31 weight % NaCl. Generally, the fluid inclusions in these coarse sparry dolomites, which often have saddle textures, have much higher temperatures than we expect from their maximum burial depths. It's implying that hot, warm fluids have entered into these systems, hotter than the adjacent carbonates, and they've moved into these higher levels, typically along focusing fractures or fault and other aquifer conduits. So if we come back and think about these subsurface burial fluids, we can have early stage eogenetic geothermal circulation, partial form of hydrothermal dolomitisation, and we discussed that in the previous chapters, the connate thermal convection model. But more typically, we can have massive margin burial diagenesis where we are compacting sediment. We can have topographic recharge, which is post-orogenic, so deep meteoric circulation. Or we can have structurally related focusing of fluids, as we see quite commonly in thrust belts. And this is the typical association that we see in a lot of Mississippi Valley type deposits. So in many petroleum reservoirs and many lead-zinc deposits, such as Pine Point and Kedgebut, and we'll discuss these a little later, we see solution driven by hydrothermal fluids as an extensive overprinting, quite often of an earlier reflux dolomite. Most examples of this extensive burial solution and diagenetic overprinting are related to the escape or the upward movement of deeper basinal brines through conduit systems, such as faults and aquifers. One of the characteristic features that we see associated with these later stage dolomites is a form of dolomite known as saddle dolomite. The name saddle comes from this very characteristic curved face morphology. They're also known as hydrothermal dolomites, and other terms used are terms like Baroque and Gothic dolomites to describe these curved crystal faces. Often associated with other hydrothermal minerals in fracture fields when we see these, so we see metallic sulfides, fluorite, which tend to be precipitated during cooling of deeper burial fluids that have invaded the carbonate reservoir. Here are some typical examples of the types of saddle dolomites, indicative of hotter and deeper fluids entering our carbonate, which may be an earlier form dolomite, it may be a limestone. We see this very characteristic zebra type dolomite texture in A. We see quite often sparry dolomite fill in fractures and vugs with this characteristic curved face as we see in B, C, and D. These are all taken in Canada, and we can see in outcrop in A, and we can see it in the subsurface in core from the Devonian. The samples that we're seeing in B, C, and D are about 2 centimeters wide for scale. We can also see it in other areas. This is some examples of saddle dolomite from Lisbon field in Utah, where something like 53 million barrels of oil and 845 BCF of gas were produced in the Paradox Fold and Thrust Belt from these Mississippian reservoirs, which generally contain evidence of a late-stage leaching enhancing porosity and permeability. So we can see combinations of late replacement and saddle dolomites, as well as solution-enhanced fractures. We see autobrecciation and sulfide mineralization, as well as the emplacement of pyrobitumens, all indicative of burial fluids moving through this system, not an early eogenetic association. Saddle dolomite is a very important form of dolomite to recognize, and it's now known that saddle dolomite typically forms with homogenization temperatures from their inclusions between 80 and 235 degrees, typically in the range 100 to 185 degrees. They range between 5 and 30 weight % sodium chlorides, so they tend to have basinal saline fluids, calcium chloride brines, and they tend to show quite depleted oxygen isotope signatures related to thermal fractionation. They also quite often are associated with strontium 87-86 ratios, indicative of input from basement. These sparry coarse late-stage dolomites can often be related to precious solution features. And so here we have an example of pre-stylolite dolomite rhombs from the lower Ordovician in Newfoundland in the figure on the left, whereas in the figure of the right we can see these syn or post-stylolite dolomite rhombs forming via processes of fluid flow associated with precious solution. The other thing that we quite often see with late-stage dolomites is some type of focusing mechanism. Quite often they're associated with faults, and we'll look at this a little later in a later chapter. this definite association with faults and the transition of textures away from the fault related to the cooling of fluids moving up and out of that fault system. Here's an example from the Variscan Cantabaran zone in Spain, just to give you the types of associations and geometries we see. The darker grey intervals here in the Badon nape are in dolomites, where they are replacing limestone along what were more permeable zones fed off a fault system with this very characteristic zebra texture, which we'll discuss a little later, indicative of hydrothermal dolomite association. So this type of replacive and void-filling dolomite is typically tied to the circulation of hypersaline and hydrothermal marine-derived brines, where the entry into the system is fed by a fault, and then it's controlled by the anisotropy in the rock poroperm in the subsurface. In this particular case, in the Cantabarian zone in Spain, we probably formed these dolomites in early Permian time, during the post-thrusting orocline formation in what was an extensional setting. The very characteristic feature we see associated with all of these late-stage dolomites is their negative oxygen isotope figures. And so here's some carbonates from this same Variscan Cantabarian zone, and quite clearly you can see that the early host carbonate has positive oxygen isotope values. But as we get into the sparry and the saddle dolomites, we see this increasingly negative association. Quite often post-dating the saddle dolomite, we will see a sparry calcite association. In general, the most characteristic feature we see associated with hydrothermal dolomites is this negative range in their oxygen isotope signatures, values of less than -8. Whereas if we look at most early stage dolomites, specifically reflux dolomites, we're typically looking at oxygen isotope values in a more positive range, typically between -4 and 8. So oxygen isotope values are one of the most useful characteristics that we can use when we study, is this sparry dolomite I'm looking at a reflux dolomite, or is it a hydrothermal late-stage mesogenetic dolomite?